from Monash University. It's my great honor to be invited to take today's presentation. Today, I'm going to share one of my studies on the topic, the global daily PM2.5 estimates and its unequal spatial-temporal disparities. Okay, good. I'd like to acknowledge the traditional owners of the land on which we meet today. I would also like to pay my respect to all past, present, and the future. Air pollution is one of the leading risk factors for premature deaths. Every year, more than 7 million deaths related to air pollution. And the PM2.5, as many of you may know, refers to atmospheric particulate matter with diameter less than 2.5 micrometers. It is even smaller than the red blood cell, so it can easily penetrate to our lung barrier and enter our blood system to affect our health. So PM2.5 is one of the most health damaging particles and affects more people than any other pollutants. Given the tremendous health impact, WHO has changed its recommended air quality guideline level. As you can see, PM2.5 with annual average have changed from 10 to 5 microgram per cubic meter. Similarly, the daily PM2.5 concentration have reduced from 25 to 15 microgram per cubic meter. However, for the environmental exposure assessment, one major challenge is the limited exposure data for both space and time scales. For example, air pollution monitoring stations are mainly distributed in urban areas. For most regions in the world, the stations are sparse or even unavailable. And also, the station data may not always be continuous or frequent enough due to the limitations in temporal coverage. Fortunately, with the improvement of the statistical and machine learning model, combined with the satellite products, the chemical transport model simulations, as well as the expansion of monitoring stations, will provide us the opportunity to predict the daily global level PM2.5 concentrations. Furthermore, as you know, air pollution are also related to the socio-economical status and residential environment. Many studies have found that low SES is more likely to suffer from air pollution, and urban-rural difference in PM2.5 exposure are also reported by many researchers. However, they still don't know whether the patterns exist in all regions of the world. So to address the research gaps, we proposed two aims in this project. The first one is to estimate the global daily PM2.5 concentrations for recent 2 decades from 2000 to 2019. And the other one is to measure the exposure inequality among the SES group and urban-rural regions. In terms of our method, we collected our data about the ground-based PM2.5 concentration from more than 5,400 monitoring stations in 65 countries and regions. We also collected the other information such as the satellite remote sensing products, the chemical transport model simulations, meteorological and land use information, etc. We use all these kind of information and put them into the deep ensemble machine learning model to finally predict a global level daily PM2.5 concentrations. These figures show the framework of our deep ensemble machine learning model. As you can see, this is a 3-stage ensemble machine learning model structure. At the first stage, we have 3 base learners, random forest, XGBoost, and LightGBM. We use them separately to predict the PM2.5 concentration. And in the second stage, we use all the predicted PM2.5 in the first stage and combine with the original features. We put them into the meta learners. Here we select the random forest and the GLM model to predict the PM2.5 concentration. At the last stage, we use all the predicted PM2.5 in the second stage and use them to put them into the NNLS, the non-negative least square algorithm, to finally obtain the optimal weight for the final PM2.5 concentration. We selected two indicators, the annual average population weighted PM2.5, PWD, and the annual accumulated population weighted exposed days to measure the exposure inequality. Here we measure the exposed days with daily PM2.5 about 15 microgram per cubic meters. After the introduction about the method section, let's move to the result part. These figures show the performance of our deep ensemble machine learning model. As you can see, our model achieved a wonderful performance with R square equal to 0.91 and RMC equal to 7.86 microgram per cubic meter, and monthly yearly exposure measurements also achieved excellent performance. These figures show the PM2.5 spatiotemporal distributions in 2000, 2010, and 2019, as well as their changes for decades. As you can see, most area in East Asia, South Asia, and North Africa have the very high PM2.5 concentration. We also found that, you see, in 2019, only 0.18% of the global land and less than 0.001% of the global population had an annual PM2.5 concentration lower than WHO air quality guideline level. And more than 70% of days in a year have the daily PM2.5 higher than WHO air quality level. We also measure the regional PM2.5 changes. As you can see, the dark line and the arrow bars show the PWD and the standard deviation, and the bar chart indicates the proportion of PED above WHO air quality level. As you can see, globally, there are more than 70% of days with PWD higher than 30 microgram per cubic meter. And we also found that, you see, the North Africa and Europe experienced a slight decline over the 2 decades. However, in other regions like Asia, the South America, and as well as Australia, experienced an upward trend during these following 2 decades. We also measure the global PM2.5 seasonal patterns. As you can see, you see high PM2.5 concentrations were observed in very high in winter in North Hemisphere, like October, November, and December. In terms of the PM2.5 exposure inequalities, we measure the air pollution in global urban, suburban, and rural regions according to 4 SES groups. We found that the high SES suburban areas experience the highest PWD with an increase in the recent 2 decades. And for the PED, as you can see, low SES and medium SES regions have the PED higher than 300 days in a year. And for the high SES regions, no matter they are urban, suburban, and rural regions, they experience an upward trend, while the very high SES regions experience a downward trend. So finally, I would like to give the conclusion. Our DML model shows good performance in daily PM2.5 estimates, and most regions in the world have the daily PM2.5 concentration higher than WHO air quality guideline level. And urban, suburban area, especially in rapid industry countries in Asia, have continuously experienced high air pollution for decades. You can find more details in our publications. And if you are interested in our deep ensemble machine learning model, you can refer to our publications in EHP. And also, you see, we created an R package called DeepO to conduct the deep ensemble machine learning model. So if you are interested, you can use this package to use the deep ensemble machine learning model to your study to help, you see, make the final prediction. Maybe it's better than what you currently used. So I would like to take a moment to thank my supervisor, Professor Yuing and Jiangning, as well. I would like to express my appreciations to the ICUC Conference Committee for your excellent platform for sharing and collaboration. Thank you for your listening.
Thank you. Questions? No? Okay. All right. So we will move on to the next presenter then. If there are no questions. House and Health, an Australian environmental health decision support